Welcome to this video on how to trisect angles. I'll begin with a very brief discussion on why people thought this could not be done, and then introduce a geometric basis on why in fact it can be done. I will then show two different methods of achieving this.
So here we've got an example of a triangle with one side length 1, the other side length 2, and the hypotenuse being the square root of 5. That's very constructible, and that's known as an algebraic number. But in addition, if we, for example, added 1 unit length to that line and had the square root of 5 plus 1, that's also an algebraic number. Most triangles, however, the side lengths won't fall exactly on an algebraic number. So that is why we consider trisection as being impossible.
Now that we understand the difficulty in trisecting an angle, what we want to do is have a look at a diagram that shows how it can be achieved. This diagram shows three equivalent right-angled triangles stacked one on top of another so that the angle at the origin is comprising of three identical angles. And this is the model that we're going to use in method 1 to trisect an angle.
So how we're going to trisect the angle in method 1 is we're going to rely on the intersection of the locus of points 2r cos alpha away from one of the lines, and that's that line there, and the locus of points 1 unit r away from the other line. You can see that those 2 points, those two lines will actually intersect on the trisection line every time. And the really good thing about this is it doesn't matter what value we choose for r, whether it's algebraic or not. Any value, such as here r prime, this is the intersection of the locus of points r prime away from one of the lines, and 2r prime cos alpha away from the other line. Now, in order to get the distance 2r cos alpha to be constructible, what we need to be able to do is we need to be able to find this angle alpha, and we will show you in method 1 how to do that. And if we can create alpha here, why can't we create it down at our origin? And the answer is we can, and we'll show you that in method 2. Okay, if I start with two parallel lines and I center my compass on one of those lines and make a circle, what we can say is that the angle here is twice the angle here.
So we've established using geometric principles of Euclidean geometry that AOB is 2 alpha and ACB is alpha. Now we can draw a line through point I co-parallel to AD and BC, and from corresponding internal angles we can say that that angle there is 2 alpha, and we can say that that angle there is alpha. So in total, between the lines that intersect at I, we've got a total of 3 alpha, and we've established therefore a geometric relationship between alpha, 2 alpha and 3 alpha, and that is how we are going to trisect angles. That is the geometric principle behind trisecting angles. The other point to note here is that the line OD is a perpendicular bisector of CE, and because DO goes through point A, AD is also therefore a perpendicular bisector of CE, and that will be used later to reverse this process in its entirety. And what we want to do now is just zoom in to that angle relationship, because that is the key to trisecting angles. Now what we need to be able to do is we need to be able to start with just the two intersecting lines that are at 3 alpha and create all of the other lines you see, so that we can completely reverse the process and complete our trisection using any angle. We are going to need to go over the geometric principles behind doing that, and there are certain Euclidean rules that we need to cover off just to make sure that we can get this done. Circle theorems are true for circles of any size. So if we know no points of intersection of the circle on the lines, it's okay to choose one to start. Angle at the center of a circle is twice the angle of its periphery anywhere in the major arc, provided both angles come from the same arc or chord. Any chord subtends the same angle at all points on its major chord, and if two chords on a circle subtend the same angle, they are equal in length. The perpendicular bisector of a chord is a line through the center of the circle. If the line is continued to the diametric point, then the arc from the diametric point to one of the circle chord intersection points also intersects the other one. When parallel lines intersect a circle, the length of the chords between the 2 points of intersections are equal. A triangle with one vertex on the center of the circle and the other two on its circumference is an isosceles triangle, so the base angles are equal and the two sides are equal because they're radii. The corresponding internal angles of a line crossing parallel lines are equal, and that's all we need. So what we're going to do now is we're going to go through method 1 and method 2 of trisecting an angle.
The first angle that we're going to trisect is this angle here. We've done an angle of 60 degrees, and that is basically because that was one of the examples they said couldn't be done. What we've done is we've done a perpendicular here that intersects at this point that we're going to label I. The angle, of course, is 60 here, so we are going to construct our two parallel lines in our circle in this area here. We're starting off, we don't know where any of the points A, B, C or D are along these lines. We know that the point O for the center of the circle, or the origin, is
so the first step is to choose point A. Every other point will scale accordingly. The second step is to drop a perpendicular from A to the line that is going to be become BE. The distance that we have between point A and this perpendicular intersection is going to be replicated around the drawing, and that will become useful for establishing all of our other points. Point A is going to be located so that the angle alpha points away from point A, and the other thing to note is that the easiest way to transfer that distance around the diagram is using parallel lines. So we're going to draw up some parallel lines along each axis, and we're going to move that distance along those lines. We're going to duplicate that distance across the other side of the line BE, and we're going to label that point F. So we make lines parallel to the existing axes so that they intersect opposite A, and unfortunately the point of intersection is not exactly point D, so we have to find another method, and we're going to go through that now. So what we're going to do is we're going to draw two lines perpendicular to the line AC, and we're going to draw them long enough to be twice the distance between the parallel lines. We're going to put it just below the intersection of the additional parallel lines that we've added, and the spacing between them doesn't really matter. I've used approximately 1 centimetre here, it could be ½ an inch or a little bit less, not particularly important. And what these are going to give us is a linear interpolation directly to E. We need to extend them out twice the length of the parallel line spacing. The next step is to duplicate the distance between the axis and the parallel line along the length of the two lines that we've drawn. The purpose of this is to give us the exact length of the required chord between point E and point C, and this will be exactly equivalent to the length of the chord from A to F. Because the chord AF subtends an angle of 2 alpha, and the equivalent length between EC will therefore also subtend an angle of 2 alpha. The next step is that we've now got the right length chord. We need to rotate it up until it's the right angle to be a chord of the circle that's not yet drawn. Now we put our compass point on A, and we rotate the points where the perpendicular lines meet the axis. And what we're doing here is we are getting the right angle of those two lines, and our next step will be to just show you again the marking of the length of those two lines up towards the right position. And the right position doesn't occur until you actually get to point E, so that's why we're using a linear interpolation. Now we'll just zoom in on that and show you that in a little bit closer detail.
So these 2 points are the intersection of 2 curves. One gives us the right distance from this axis here, right across and over to there, and the right angular aspect relative to point A up here.
We draw a little line connecting those 2 points, and that gives us our exact value of E. Now that we've got the value of E, we can connect our compass to point A again and rotate that across to the other axis, which gives us exactly point C. Now that we have the correct positions of point C and point E, we can draw the chord in between those 2 points. We know that the perpendicular bisector of this chord will go through the origin, point O, and will connect up to point A as well. We use our compass to mark up the perpendicular bisector, and then we'll draw a straight line using the straight edge.
We've now got our origin, point O. We'll label this intersection point I. Let's draw our circle.
Completing the circle gives us point B, so we are able to draw line BC. that slopes at an angle of alpha relative to the axes. Now we need to just choose a value of r, approximately a third of the distance between the two lines. We need to then transfer that distance along the axis using parallel lines. Once we have transferred the distance r close to the intersection of the two axes, we can transfer the distance r from one axis to the other just simply by putting our compass point at the intersection and rotating the 2 points across to the other axis. We can then transfer the distance r along the bottom axis using parallel lines as we did on the top axis. We can transfer the distance r now onto the line that is on an angle of alpha. We can double the distance r along this line, and that gives us a distance of exactly 2r cos alpha away from the bottom line. Make a parallel line at the distance 2r cos alpha away from the bottom line, and the intersection of 2r cos alpha from the bottom line and r from the top line is our trisection point. And we just need to join the origin to the trisection point, and that is alpha.
Now all we need to do is bisect this angle, this remaining angle, and we've completed the trisection.
So this is method 2 of trisecting an angle. It will become the preferred method because it's a little bit less complicated. So just like in method 1, the first step is to choose point A, drop a perpendicular bisector from A to the adjacent axis, allowing the length of that line to proceed through twice the length from A, and mark off the length that's twice the distance from A. Again, allowing the length from A to the perpendicular to be our line measurement that we move around the diagram with parallel lines. Again, we create our perpendicular lines just past the point where the parallel lines intersect.
And so I've made two arcs from point A to nearly this point C, and meeting those arcs up against the right distance. So that gives us the right angle, and our arc from here to here gives us the right distance. So these arcs here give us the right angle, and these arcs here give us the right distance from the axis down here, from this axis here. So if we interpolate those 2 points up to this axis here, that gives us up to this line here, that gives us the correct point E.
With an arc centered on A, we transfer point E over and find point C, and then we can draw a line between the two. Using the compass, we set up for the perpendicular bisector of EC, which runs through to point A. Using our straight edge, we draw the line from point A to the bisector of EC. This passes through the origin, giving us an accurate position for point O. So now we have point O, we were able to draw the circle, and completing the circle gives us point B accurately.
Bigger. C is there. This is going to be point B. Label this point here as point F.
Now we can draw the line BC, noting that it is the second of our parallel lines at an angle of alpha.
Okay, you're defining theta. The next thing is to draw the line of this, the line that has this angle through the centre of that circle, and that's our first trisection line. So that is our first trisection line, and the easiest way to get the other trisection line is just to halve this angle between here and here. It's one of our points.
So now we can trisect an angle. There are certain things that follow these corollaries listed, plus there's another corollary that I want to discuss in a completely separate video. So like and subscribe.